Hi, this is John Isles and welcome to Geometer's Paradise. Today we're going to be talking about related conditionals, but we need to start with just a review of what makes a conditional statement special. Remember that a conditional statement is declarative in two parts. The first part is called the hypothesis and the second part is the conclusion. We learned from our lesson on detachment that satisfying the hypothesis causes the conclusion to result. So in this particular case, M is the midpoint of AB is the hypothesis of our statement, and AM equals MB is our conclusion. The first of our related conditionals is called the converse. The converse means switch the hypothesis and the conclusion of the statement. So the converse of if M is the midpoint of AB, then AM equals MB is if AM is equal to MB, then M is the midpoint of AB. We write the inverse of a statement by negating the hypothesis and the conclusion. So if M is the midpoint of AB becomes if M is not the midpoint of AB, then AM is not equal to MB. The contrapositive is a combination of both the converse and the inverse. When we write the contrapositive of a statement, what we're going to do is switch the hypothesis and the conclusion and negate the hypothesis and the conclusion. So if AM is not equal to MB, then M is not the midpoint of AB. And this is how you write the three types of related conditionals. What we want to look at next, I guess we can do this in review. To write the contrapositive, you need to, now this is contrapositive, you need to switch and negate the hypothesis and conclusion. To write the converse, you need to switch the hypothesis and the conclusion. And to write the inverse, you need to negate the hypothesis and conclusion. There we go. All right, now, is it true? So here are the statements we wrote earlier. The original statement is true. By definition, if M is the midpoint of AB, then AM is equal to MB. This is a true statement. But this one is not true. If AM is equal to MB, then M is the midpoint of AB. This is actually a false statement. Wow, I cannot type. And check out what we can do here. If I draw a line segment, here's AB. All right. And for the sake of argument, let's rename this to M so that it matches what we're doing. Let's draw a circle from M to A. Okay? Now, if I put another point on the circle and I connect the dots, then AM and MB are equal to one another. And as I move it around, all of these versions of BM is equal to MA. All right, so this drawing is a counterexample for the converse of the midpoint definition. So false, we can draw it as an angle. Okay. Inverse, if M is not the midpoint of AB, then AM is not equal to MB. So can we draw anything where M is not the midpoint of AB and AM is equal to MB. Okay? And this same drawing fits. All right? In this particular case, M is not the midpoint and AM is equal to MB. So since this drawing invalidates the conclusion of the inverse, that means the inverse is false too. False, same as converse. The same counterexample works for the converse as it does for the inverse. Finally, the contrapositive, if AM is not equal to MB, then M is not the midpoint of AB. And this one has to be true. The reason why it's true is that it's implying that AM being equal to MB is a necessary condition for M to be the midpoint. So if AM is not equal to MB, then the necessary condition for midpoint, that they are equal segments, is not met. So this is also a true statement. If it's not equal to MB, then M is not the midpoint of AB. Okay, now here's a ridiculous one. If an animal is a rodent, then it is a mouse. This is false. A rabbit is a counterexample. Okay, a rabbit is a rodent. It is not a mouse. If an animal is a mouse, then it is a rodent. This is a true statement. A mouse is a type of rodent. If an animal is not a rodent, then it is not a mouse. So if you are not a rodent, can you be a mouse? The answer is no. So that means this is true, because if you're not a rodent, you're not a mouse. So this is a true statement as well. And if an animal is not a mouse, then it is not a rodent. Again, can we think of an animal that is not a mouse, but it is a rodent? Okay, so false. Rabbit works again for this one as well. All right, now let's look at the truth values. Up here, the original and the contrapositive are both true. The converse and the inverse are both false. Down here, the original and the contrapositive are both false. The converse and inverse are true. It turns out that original statements and their contrapositives, converses and inverses, are what we call logically equivalent statements. So that means that if one is true, the other will be true as well. The importance of this is that sometimes we might try to write a proof for a statement, a conditional statement, and it proves to be very difficult. But if we look at the contrapositive of the statement, it might be that the contrapositive is very easy to prove. Converses are important when we start thinking about what we're going to talk about next, which is biconditionals, because sometimes you want to be able to work a conditional statement forwards and backwards. And that's when we run into converses. But contrapositives are very useful for trying to prove original statements that are very hard to prove on their own. All right, I said biconditional just a few minutes ago. A biconditional is a statement that's true when both parts of the statement and its converse are true. So, for example, if two lines intersect to form congruent angles, then the lines are perpendicular. The converse is if two lines are perpendicular, then they intersect to form congruent angles. Now, we know that both of these statements are true from our work with perpendicular lines during Unit 2. All right? We can write a biconditional using the if and only if format because they are both true. We can say two lines intersect to form congruent angles if and only if the lines are perpendicular. If and only if can be abbreviated to IFF like it is in this line. If you don't want to write it all the way out, you can just write IFF. Okay? Showing a biconditional requires proving both parts of the biconditional. You have to prove it forwards and backwards. So one statement that you would have to be proved would be if two lines intersect to form congruent angles, then the lines are perpendicular. And then you have to turn it around and show that if two lines are perpendicular, they intersect to form congruent angles. All right. So let's look at the converse of the midpoint. If AM is equal to MB, then M is the midpoint of AB. And we learned earlier that this cannot be true. This is not true because the converse is false. All right, I can draw that angle. You remember the one here. This drawing is the counterexample for the converse. So we cannot do an if and only if for this statement because it's only true one way, whereas this statement is true both ways. Okay, your practice problems will be here at the end of the 3-3 related conditionals unit. You're going to be writing converse, inverse, contrapositive, analyzing the statements to see if they're true or false, and then validating whether or not they are can be a biconditional. Here we have the perpendicular line statement. Here, segment addition postulate, and then some kind of ridiculous statement about trees falling in the woods, and finally a bisector statement. So good luck, and I'll see you in class.